Okay, so this is the first of two videos which I'm going to generate to explain how to use Lewis diagrams to determine the shape of a molecule. The rules that I follow for drawing Lewis diagrams are as follows. The first thing you want to do is determine the total number of valence electrons that you have. So that's this rule number one here. The second thing you want to do is to pick the symbol which is going to go at the center of the Lewis diagram. And that typically is the first element which comes in the formula of the compound. So that will make sense as we look at a particular example. Then what I do is I assign bonding pairs of electrons first, and I just use lines to represent those because if you don't use lines, it tends to become particularly messy as the molecules get more and more complex. So use lines for bonding pairs. Number four then is to assign electrons to the outer atoms finally, and then the final step is to check that each element has a share of 8 electrons, which is observing the octet rule. So the best way to explain how to do Lewis diagrams is to just take particular examples. And I've set up this little table. So what we're going to do now is we're going to do a Lewis diagram of a compound. We're going to count up the number of electron clouds that it has around its central atom. And then we're going to discuss the possible shapes and molecular polarity. So there's quite a lot to this video, but it works best if it's all taught in the same all together and in one comprehensive table of information. So if we start off with CO2, carbon dioxide. So on the periodic table, carbon's in group 4, so it'll have 4 valence electrons or 4 outer shell electrons. And oxygen is in group 6, so it'll have 6, and times 2 because you have 2 of them. So in total you have 6 times 2, which is 12, plus 4, so you have 16 valence electrons in total to arrange in the Lewis diagram for CO2. So the next thing I said was step 2 was to determine which element was going to be at the center of the Lewis diagram, and I said if typically it's the first element in the compound's formula, so in this case that's going to be carbon. So carbon goes in the center. Now whether you put your oxygens here, here, or if you want to arrange them that you put your oxygen down here, that doesn't matter. But as you get used to doing these diagrams, you'll soon realize the actual position that these elements will end up being in when they follow their shape. So I'm going to put my 2 oxygens just evenly either side of the carbon. What I'm going to do is I'd assign a bonding pair next. So a bonding pair, one line represents 2 electrons, one shared between one from carbon and one from oxygen, and then another bonding pair between the other carbon and oxygen. Now that leaves carbon with just a share of 2 and 4, so 4 electrons altogether, which is not 8. So what we do is we put in a double bond here and another double bond there, and now carbon has 2, 4, 6, 8 electrons, and it's happy. Okay, and then we want to look at the outer atoms now, and remember that we've 16 electrons to use up altogether, and we've already used up 8, so we need to use up another 8. So 2, 4, 6, and 8. And then if you count up for your oxygens, you'll see that it has 2, 4, 6, 8 as well, and oxygen over here has a share of 2, 4, 6, and 8. So that compound is complete. We've used up our 16 valence electrons, and that is a Lewis diagram for carbon dioxide. Now the next step is to count up the number of electron clouds, and I'm just going to use a different color for this. Electron clouds are essentially areas of electron density which surround the central atom. So the central atom in this case is carbon. Now this double bond makes up 1 electron cloud, and this double bond here makes up another electron cloud. So you can actually draw little clouds around it just to emphasize the point. Now electron clouds can be bonding pairs of electrons, or in some cases non-bonding pairs of electrons, as we will see as we go through this video. So we have electron clouds in this particular example. So the only possible shape for a compound with 3 atoms, so 1, 2, 3, and 2 electron clouds, is a linear shape, described as being linear. So linear is where the 3 elements form a line, straight line. That's the case for carbon dioxide. The angle of a linear molecule is going to be 180 degrees. And the next thing we want to talk about now is the polarity of the compound. So the first thing I need to explain is what is a polar bond. Well, a polar bond is essentially established between 2 elements which have different electronegativities. So if you look at carbon and oxygen on the periodic table, carbon is not as far to the right on the periodic table as oxygen is, which makes oxygen more electronegative, slightly electronegative. So we use the delta negative symbol for that. Carbon is therefore slightly positive, and this oxygen over here is also slightly negative. Now there's another symbol you can use to represent the distribution of electrons in a polar bond, and it's this arrow here, where the end of the arrow here, if you notice, it forms a positive sign, so that's where the positive end is, and then the head of the arrow is where the electron density is moving towards in preference, based on the oxygen being more electronegative. So this is a polar bond. Now, a common misconception among students is that if a molecule has a polar bond, that makes the molecule polar overall, which is not the case at all. You have to look at how those polar bonds interact with each other. Now, in this case, you can see that there are two polar bonds pulling in opposite directions. So the dipoles, we call these arrows dipoles, the dipoles cancel because they're pulling in opposite directions. And as a result, you have what they say a symmetric distribution. I'll just explain this for the first one, and then we can just refer back to it for the rest. Symmetric distribution of electron density. So what we're saying is you have an even distribution of electron density either side of the carbon. So that's symmetry, the same on both sides. That's what it means. You could draw a line of symmetry down the middle of the molecule there. So symmetric distribution of electron density and the dipoles cancel. So as a result, this is a non-polar molecule. Okay, and you go through the same arguments every time you want to explain whether a molecule is polar or non-polar. You talk about whether there's a polar bond, you then discuss whether the dipoles cancel or not, you discuss the symmetry of the electron distribution, and then you make a final decision whether the molecule is polar or non-polar. So that's the first simple example, just a Lewis diagram for carbon dioxide. It only has two electron clouds and there's only one possible shape, which is linear. So with that understanding in mind, we can move a little bit quicker with our next examples. So we're going to move on to a 3-electron cloud situation. 3-electron clouds. And the first example we can do is BF3. So I'll just go back to my black pen here. So BF3. Boron has only got 3 valence electrons. Fluorine has 7 times 3. So in total you have 24 electrons. Valence electrons. Put boron in the center because it's the first element in the compound's formula, and you put fluorines arranged around that. Then just assign bonding pairs first according to our rules. Now boron is a moron. Boron only wants 6. So with 6 electrons, boron is actually satisfied. So it's an exception to the octet rule. Okay, so boron only wants 6, so it's happy, in which case fluorines just need to get 8 altogether. So we put 2, 4, 6, and then 8, 2, 4, 6, and 8, 2, 4, 6, and 8. Now notice I take the time to put all these lone pairs or non-bonding pairs of electrons on each of the fluorines. You must do that to get the correct Lewis diagram in your assessment. Do not get lazy and eliminate them, because it's these lone pairs of electrons which influence the overall shapes that we're talking about here. So for boron trifluoride, the shape is going to be dictated by the fact that there are 3 electron clouds around the central atom. 1, 2, 3. 3 electron clouds. So the shape for that is called trigonal-planar. Trigonal-planar, and it's just as I've drawn it already. The bond angle is going to be 120 degrees. And that's the same here, 120. And that's your trigonal planar format. Now, just to talk about polarity of a trigonal planar molecule, well, in this case, we do have 3 polar bonds. So the fluorine is the most electronegative element in the periodic table, so it's going to be where the electron density is moving towards. But if you notice, the polar bonds are pulling in opposite directions. Okay, so the polar bonds are cancelling again. Okay, and as a result, you have a symmetric distribution of electrons, just as in CO2, and as a result, the molecule is also nonpolar. So BF3 is nonpolar. Now, I have this simulator open here, this is from Colorado University, and it's called PhET. They do many different simulations for aiding student learning of scientific concepts. But if you just Google molecular shapes, so you can see it up the top here, if you Google molecular shapes, you will come up with this particular piece of software, and you can download it and run it yourselves on your computer. So I just want to go through this and show you guys how useful it is. So if we do CO2 first, all right, CO2 looked like that, and you can see you can manipulate your molecule in 3 dimensions. The blue one would represent carbon, and the 2 grey ones would be oxygen. You have your double bonds there, and down the bottom here it tells you the molecular geometry, which is linear. Now, if we remove those double bonds and we replace them with 3 single bonded fluorines, so in the case of BF3, well, you can see that the molecular geometry is now changed to trigonal planar, and it's quite easy just to play around with the molecule. And this piece of software becomes particularly powerful when we're dealing with more complicated molecules. So I'll return to this from time to time during my explanations. All right, so back to 3 molecules with 3 electron clouds. Now, there's another example we can look at with 3 electron clouds in it. But in this case, we're looking at, instead of 1, 2, 3, 4 atoms, we're going to look at 3 atoms. Okay, so 3 electron clouds and 3 atoms. An example of this is sulfur dioxide. So again, if we do our Lewis diagram, sulfur has 6 electrons. Oxygen also has 6 valence electrons times 2, and that gives you a total of 18 valence electrons to distribute. Sulfur is the first element in the compound's formula, so we put sulfur in the center, 2 oxygens around it, and then we put some single bonds together. Sulfur only has a share of 4 electrons in that case, so if we put a double bond on here and then put a lone pair on the top. Now, sulfur is one of those that you get to know. The double bond could have easily been placed on the other oxygen, so it's just indifferent which one it goes on. The oxygen here now has 2, 4, 6, 8, and this oxygen has 2, 4, 6. Squeeze them in there. 6, 8. So 2, 4, 6, 8, 10, 12, 14, 16, 18 used up our 18 valence electrons. Now, just to show where the electron clouds are again. So in this case, we have 3 atoms, 1, 2, 3, and we have 1, 2, 3 electron clouds all together. So we're looking at another example of 3 electron clouds. In this case, we have 3 electron clouds and only 3 atoms, right? So you need to memorize these shapes essentially. So 3 electron clouds plus 3 atoms gives you a bent shape. It's also known as angular, and it's also referred to as V-shaped. Okay, and so the shape is bent. Instead of being linear like CO2, it's bent. Lone pair still up there. Now, to talk about the polarity of this compound, well, the sulfur is not as electronegative as the oxygen. So you can see here that the dipoles are not cancelling each other out because they're both pulling down towards the same end of the molecule. If I draw that shape around it, you can see that there is an overall negative end and there's an overall positive end. So you could draw a net dipole for this molecule, and there would be a movement of electron density in one direction. So the polar bonds don't cancel in this case. There's an asymmetric distribution of electrons, electron density, and therefore the molecule is polar. So that's our first polar molecule that we've come across, and that one is described as angular or bent or V-shaped with a net dipole. So this is described as a net dipole or a molecular dipole. Now, if we go back to our PhET simulator, so for SO2, we want to remove everything just for a second. We want to put a double bond in, we want to put a single bond in, and then we add our lone pair, and that gives us our bent shape down here. So you can manipulate that molecule. This blue one would be represented by sulfur, or is representing sulfur. The two grey ones are oxygen again, and here's your lone pair. So you can see the importance of including your lone pair. There's a theory called valence shell electron pair repulsion theory, or VSEPR, and it's these lone pairs of electrons plus bonding pairs repelling each other that influences the shape of this molecule. So currently it's bent. If I remove the lone pairs, watch what happens to shape. It becomes linear. So the lone pairs have a big influence on the overall shape of the molecule, so don't eliminate them when you're drawing your Lewis diagrams. Now if I come back to our shapes, the last scenario we want to look at for level 2 is if we have 4 electron clouds surrounding the central atom. So I'll just do the first one and then we'll probably have to move on to the new page. We're looking at 4 electron clouds, and in this case for the first one we're going to look at 5 atoms. So 4 electron clouds and 5 atoms. An example of that, which exam papers like to talk about a lot, is we'll do 2 of them. We'll do CHCl3 versus CCl4. This is a common question which appears on exam papers. So for CHCl3, central atom is carbon. It doesn't matter where you put the hydrogen, but there's also 3 chlorines. And then you have 1, 2, 3, 4, and then each of the chlorines will have their 8 electrons. Didn't leave much space for that. Okay, but each of the chlorines has a share of 8. The hydrogen only wants 2. In this case, we just have 4 chlorines. Put in your lone pairs, don't get lazy. Becomes more tedious as you have more lone pairs to add, so you can see what temptation is to stop doing it. So we're still talking about CHCl3 versus carbon tetrachloride. So in this case we have 4 electron clouds and we have 5 atoms. So just there's my electron clouds, 1, 2, 3, 4 around the central atom. Again, 1, 2, 3, 4. So we have 4 electron clouds and 5 atoms. So the shape here is a tetrahedral shape. Tetrahedral. Now to draw that using dashes and wedges, well, you put your carbon in the center in both cases. You put 2 bonds which are in the plane of the page, so we'll call that one Cl and H. On this side it's going to be 2 chlorines. So 2 bonds in the plane of the page. We'll use a wedge which is filled in. That represents a bond coming out of the page. A wedge again here. Notice that the wedge is a little bit offset. It doesn't sit vertically beneath the carbon. Again, there's a chlorine in that. And then we want to use a dash which gets increasingly bigger as it disappears into the background. That represents a bond which goes away from you. Again, a dash on this side, increasingly bigger, bond going away from you. So, common question you'll be asked in exam papers is to decide which of these 2 compounds, CHCl3 or CCl4, is a polar molecule overall. So I'll use a green color this time. So both compounds have polar bonds. The CHCl3 has 3 polar bonds, whereas the CCl4 has 4 polar bonds. The difference between carbon and hydrogen is not significant enough to say that you have a polar bond. So in the CCl4 situation, you have 4 polar bonds. Now these polar bonds, the polar bonds are pulling in opposite directions, so the polar bonds cancel. They cancel each other. And as a result, you have a symmetric distribution of electrons as before, electron density, and as a result, the molecule is nonpolar. Whereas with CHCl3, you can see here that the dipoles are not cancelling. So the dipoles don't cancel. And as a result, you have an asymmetric distribution of electrons, electron density, and the molecule is polar. So it's incorrect to say that every time you have a tetrahedral shape, you're going to have a polar molecule or a non-polar molecule. You have to look at the particular example and decide for yourself based on the elements involved. Now that is the first of the 4 possible shapes you can have for 4 electron clouds. So I better do the other 3. we're going to need a new page. So if I set up a new page, right, I just noticed that I forgot to complete adding bond angles to these molecules as well. So the bent or angular shape for the 3 electron clouds tends to be a little bit less than 120 degrees. I'll just use yellow. So it's a little bit less, it's going to be less than 120. The tetrahedron, it's always 109, okay, 109 degrees. So that's what you need to add for a tetrahedron. And if I go to my molecular shapes simulator then in FET here, so we did, the last one we did here was bent, so we need to do a tetrahedron, and this is going to be we'll just remove all now. We add 1, 2, 3, and 4 bonds, and there's the tetrahedron. So you can see here, if I align this molecule up just to illustrate the use of dashes and wedges as well, probably put it just like, well, behave yourself. Where is it going? Yeah. Okay, that's more like it. All right, so these 2 bonds here would be in the plane of the page, so you just draw straight lines for those bonds. This bond is coming at you, so that would be a wedge that you draw coming at you, and then this would be a dash which is going away from you into the plane of the page. But that's your tetrahedron, and we had CHCl3 versus CCl4 for that scenario. So just to go back here now, we're going to complete our 4 electron cloud situation. So we have 4 electron clouds. The next molecule we want to look at is NH3, which is ammonia. In this case, we have only got 4 atoms, whereas before we had 5. So for 4 electron clouds and 4 atoms, I'll quickly draw the Lewis structure for ammonia. So you have 5 electrons plus 3 times 1, which gives you 8 electrons to deal with. So ammonia wants to have 2, 4, 6, 8, and each hydrogen is satisfied, and that's your 8 electrons. Now this shape is known as trigonal pyramid, or some books use the word pyramidal. No, that's how I learned it originally. So trigonal pyramid or trigonal pyramidal. So the shape for a trigonal pyramid is essentially a triangular shaped pyramid. You have 1 hydrogen which is in the plane of the page, you have 1 which is coming out towards you, and then you have one which is going away from you. And don't forget your lone pair at the top. Now the polarity of this compound should hopefully be pretty obvious to you guys now at this stage from what we've been talking about. You have all the electron density moving towards one end of the compound. The dipoles do not cancel, so this is a polar molecule. So ammonia is polar. If we quickly look at ammonia is bond angles, and the bond angle in ammonia is going to be slightly less than a tetrahedron, and that's because of this lone pair of electrons repelling the bonding electrons and making it slightly smaller. So it's less than 109, and in fact for ammonia the bond angle is 107 degrees. And that's the reason why it's slightly smaller than in the tetrahedron. So then if we jump to FET just to look at ammonia, well, ammonia we want to replace a bonding atom with a lone pair instead, and then you get your trigonal pyramid down here. So that's ammonia there. Nice simulation. You guys can play around with this yourselves. It's totally free, which is great. Okay, so that's ammonia. Now we go back to here. We got to finish off. We do. I want to go to 4 electron cloud still, and we're going to go for 3 atoms. An example, a good molecular example for this is H2O. So water. So we have 2 times 1 plus 6 from the oxygen. That gives you 8 electrons to distribute in its Lewis diagram. In this case, the first element in the compound is not in the center. It's actually the oxygen which goes in the center. Typically the one which is on its own will go in the center, and then if there's multiples of the other atoms, they're arranged in the outside. You start off with a bonding pair between each. The hydrogens are satisfied, which means the remainder of the electrons must be non-bonding and on the oxygen. So that's your 4 electron clouds right there. Okay, 4 electron clouds and 3 atoms. So the shape for this is angular, bent, or V-shaped, which was just like for SO2. But the difference here is that we have 2 non-bonding pairs of electrons instead of 1. So in this case, the bond angle for water with its 2 non-bonding pair of electrons is smaller. This bond angle is smaller versus for SO2 because it only had 1 bonding pair of electrons. So that angle is less, smaller bond angle, and it's because of the lone pairs times 2 for H2O. The bond angle for water is about 105 degrees. I think I said SO2 was 120. I think it was a wee bit over with that one, but it's definitely greater than the bond angle in water. What is water polar? Should be easy to see there. Electron negativity or electron density is moving towards the oxygen. In both cases, the dipoles don't cancel, so this is polar. Water is definitely polar, and is one of the reasons why it's such a good solvent for so many ionic compounds. We continue our table on down, and we're nearly finished. The last scenario we want to look at will be 4 electron cloud batteries. And this is example for this is HCl. So in this case, hydrogen is 1, chlorine is 7, so 8 valence electrons. Doesn't matter, there is no element to go in the center here, but you do need to make sure you have 8 electrons in your Lewis diagram, which we do. The 4 electron clouds may not be that obvious to see initially, but they're here, 1, 2, 3, and 4. So that's your 4 electron clouds in your 2 atoms. This shape is linear. Okay, and HCl should be easy to see that it's polar. There's only one polar bond, so it can't be cancelled out by another, so it's a polar molecule. And just to finish using FET, H2O, then we removed another bonding pair, so remove that, and then we added another lone pair, so that's bent, angular or bent. So this would be H2O. Let me just rotate that a bit better for you. Okay, so that's your H2O. This would be your oxygen. This is your 2 hydrogens. These are your 2 lone pairs. This bond angle is not as big as the SO2 situation. So if I remove 1 lone pair, that's really nice. You can see that the bond angle relaxes a bit and gets a bit bigger, and this is the situation for SO2. So that's the beauty of this simulator. And then the last one we did there was HCl. So HCl just had hydrogen bonded to chlorine, so we remove, go away, yes, and we wanted to add, okay, so that's linear. So 3 in total, 1, 2, 3, 4 electron clouds around the central atom, the chlorine in this case, and that's the completion of our Lewis diagrams for 2, 3, and 4 electron clouds around the central atom, and we've talked about all the shapes, we've talked about the bond angles, and we've talked about the molecular polarity. So that is a comprehensive review of Lewis diagrams and molecular shapes.